Okay, so there is a kind of useful theorem for figuring out limits that's presented at the end of section 2.3. This is called the Squeeze Theorem. It's got a lovely name. And it goes like this. If you have three functions that are related by this inequality, I've named the functions h, f, and g. So f is the function in the middle. On the outer, we have h of x, which is less than f, and g of x, which is greater than f. And this is for all x near c, except possibly at c, because as always, we don't really care what's going on at c. We just care what's going on nearby as we approach it. And if the limits as x approaches c of the lower function h and the upper function g are both the same, equal to L, then the limit of the middle function, which is squeezed in between them, as x approaches c, will also be equal to L. So we can draw a picture to sort of describe this. Let's say h of x is going to be purple. That function is sort of on the bottom. And then we have g of x, which let's make g of x red. That function will be on top. And they're going to have the same limit as x approaches c. Let's put c right here. If they have the same limit as x approaches c, then they should be doing something like that, right? They're both, we've got g of x up above and h of x down below, and they're kind of squeezing together at c here, right? So then L would be that height right there, that y coordinate of this point that we're approaching. That's the limit L. What this theorem is saying is that if you have this f of x function, which is sort of in between here somewhere, if it has to be in between, it will get squeezed in here so that its limit is also equal to L. Okay, that's what it says. So let's do an example of this. Now, one type of function which really lends itself to applying the Squeeze theorem is like a sine or cosine function. Because sine and cosine functions, we know that their values are bounded between -1 and 1. Now, the fact that we have those bounds up and above and below, -1 and 1, that's a lot like the Squeeze theorem. It's like saying, hey, look, we're between -1 and 1. Now, -1 and 1, though, never meet each other, right? So they never have the same limit. So the -1 and the 1 would be just two lines. You can't apply the Squeeze theorem there. But if you do something to it, if you make that function a little more interesting, maybe with a product, then you can get something pretty neat. So we're gonna use this function, which we have actually looked at before, or something very similar to it, maybe not this exact one. If you'd like, you can graph this on Desmos and see see kind of what it looks like. So this is x squared times sine of 1 over x. All right. So I choose this because note that the limit as x approaches 0, is where we're going here, is 0, of sine of 1 over x. Note that that limit does not exist. Okay, that makes this a more interesting problem, because I mean, if I just did sine of x, then this would be kind of boring, because sine of x is continuous at 0, so we could just apply the idea of distributing a limit across a product and then using continuity. So I specifically chose the sine of 1 over x so that we would have a situation where that second factor in this product, the sine part there, its limit doesn't exist. So we can't just apply the product rule and like take the limit of each factor function. We can't do that. Or I mean, like, yeah, we can't, because that second one doesn't exist. So what we can do instead is we're going to back up a little bit, start looking at that sine function. Hang on a second, I'm just going to close my room door here. All right. Now that sine function, no matter what x equals, with the exception of 0, whatever is going on in there this is a sine of that, right? And we know that the outputs of the sine function, regardless of what the inputs are going to be between -1 and 1. So we can say with confidence that this is true, right? Any sine function, no matter what you stick inside it, is going to have outputs within this range. Okay, and that's for all x except 0 where it's undefined. Therefore, what we can do is multiply all three sides of this inequality by x squared. So we'll have -x squared is less than or equal to x squared times sine of 1 over x is less than or equal to positive x squared. And that is since x squared is going to be greater than 0 for all x that aren't 0. Okay, we're multiplying all three sides of this inequality by a positive number. So we don't need to worry about flipping the inequality symbol around when we multiply by a negative. That's not going to be an issue here with x squared. If, by the way, you were just multiplying by x, then you'd have to kind of break into cases and be like, well, here's what it looks like if x is positive, and here's what it looks like if it's negative. And they're very similar, but technically you do have to break it up. But not this time. So what we have then is we can look at the limits of the function on the left and the function on the right as x approaches 0. What's the limit as x approaches 0 of -x squared? It's just a polynomial. So that's just going to be -0 squared, right? Which is just 0. And also, the limit as x approaches 0 of the function on the right, which is positive x squared, is also equal to 0. So we are in this scenario where our function which is on the bottom and our function which is on the top have the same limit as x approaches 0. And this x squared sine of 1 over x is squeezed in between them. So therefore, it is going to have that limit as well. So I'll finish by saying, thus, limit as x approaches 0 of the middle function, x squared sine of 1 over x, will also equal 0 by the Squeeze theorem. And we're done. So we were able to show that this limit equals 0 using that Squeeze theorem.